So I'm going to be talking about LLM-Modulo framework as compound AI architectures for robust planning and reasoning. I kind of avoided using the word neuro-symbolic because it's a rather a kind of a loaded word. I don't completely understand what it actually means. I think Henry gave like a large taxonomy before early in the morning. But what I would try to do is I'll try to kind of give two important interpretations, and I do deal with them, those two interpretations. I basically sometimes think neuro-symbolic seems to be sort of trying to make fetch happen because deep learning is working well. So how do we get symbolic back in? I think there is a much more meaningful way from my perspective to bring it in. And I actually differentiate into these ways. One is that you might very well want to separate internal symbolic reasoning versus external symbolic interfaces. I personally don't quite know whether internal symbolic reasoning is really needed in a system to be able to reach human level intelligence. But whatever representations systems use internally, AI systems must provide an external symbolic interface to us. And that is a good enough reason to understand neuro-symbolic reasoning as far as I'm concerned. That's like one very important reason. So we don't want to deal with the AI systems by getting explanations from them, by pointing and then giving advice to them by nodding, which is basically what RLHF winds up being. We do want to kind of deal with AI systems the way we deal with other humans. And so this is one direction that my work has been looking at, explanations by converting internal rationale into local symbolic models, because humans understand language is symbolic to a large extent. And so we kind of exchange information predominantly through symbolic means. And also learning to accept symbolic advice. The machines should be able to accept advice from us in terms that we want to give, rather than going into the internals and changing the layer activation in the 174th layer. I think it's like a really sad way to live life, and if in fact we are going to spend our time trying to make sense to the AI systems. I have hard enough time making sense to people around me. I don't want to make my life any much harder. Okay, so that is like one big reason why you would be interested in symbolic neuro-symbolic reasoning. And that is actually not the main topic of today's talk, but I want to show you that I want to give you a couple of references from my group's work. There's a Blue Sky paper in IIII 2022, which sort of talks about this view. There's a book on explainable human AI interaction that you can get it from the archive. It's free now. And also there is a talk with the QR code, which basically talks and 1 hour talk about this view of neuro-symbolic reasoning. Now, the second view, which is actually a lot more, which is also equally important in my perspective, which is like very useful reason to think in terms of neuro-symbolic systems, is that you want to somehow combine things like LLMs, which everybody is talking about, with the advances that have been done before. So if you think about it, and I'll come back to this in a minute, all of AI before LLMs is a deep and narrow, is an approximation to deep and narrow system 2 kind of reasoning. And suddenly LLMs came along, and they're really very good at broad and shallow system 1 type reasoning. So there should be a way in which we can combine system 1 and system 2. And in fact, Henry was talking about this too earlier, but I would go beyond that and say that it's kind of rather depressing to say that the way neuro-symbolic AI would work is to actually make a unidirectional pipeline. Like LLM takes the problem specification, converts into SAT or PDDL or something, and gives it, throws out the wall to some symbolic system, which then tries to solve it. That seems to be, yes, it's kind of an integration, but it's like less interesting integration from my perspective. And it doesn't, in particular, change the limitations that we do know exist for symbolic, like the system 2 AI systems, the symbolic AI systems. They are good at giving formal guarantees, but they're also tend to be very limited in scope in terms of, you need to make sure that the specification you gave corresponds to the language I can handle, then I will give you the guarantees. And I think the interesting way to combine LLMs and LLMs sorts of things and the advances pre-LLM in AI. And by this, I basically mean pretty much everything. Probabilistic systems are also essentially symbolic systems, and so you want to combine these in a bidirectional fashion rather than a single directional interaction. That's what LLM-Modulo architecture is, and that I'm going to try to get you to understand a little bit. But before we get there, I will be making this discussion mostly. There's been one interesting question has been on everybody's mind, really, is can LLMs plan? Because the point, of course, is we kind of know that they are the best system one approximations we ever made. They're like broad and shallow system one approximations that we ever made. And the question is, can they somehow magically also do planning and reasoning, which typically have been associated with system two brain? So if you know the Kahneman metaphor, there is basically the system two and the system one, and we have both, and there is an interesting combination, bidirectional interaction between system two and system one in our own in this metaphor for humans. But if you look at LLMs purely by themselves, they're like a giant external non-veridical system ones. For the entire humanity. They've been trained on the entire digital footprints of the whole of humanity, and there is upfront no reason to believe that they will be doing system two abilities unless somebody's system two got compiled into LLM system one. And so they're doing reasoning by retrieval. That means they're not reasoning from first principles. They're essentially assuming that this problem must have been solved before. Can we approximately kind of retrieve the answer to that? On the system two, system one side for the humans, we do this. In fact, when we solve a problem, we memorize it and we try to remember this so that next time we don't have to start from scratch. The crazy thing about LLMs is they don't actually have a separate system two. They're dependent on our system twos, which is either humans or outside symbolic or system two solvers. So given this, I assumed from the beginning that probably LLMs can't do planning. But then everybody has been jumping up and down saying LLMs are doing reasoning, LLMs are doing planning. If you look at any random NeurIPS paper, it's full of these kinds of claims. And then, while anthropomorphization has been a sin, for AI forever, it's been on steroids with LLMs because every paper starts with like humans, LLMs, blah, blah, blah. And then most of those arguments wind up not holding water if you actually carefully look at it. So at any rate, back in like 1.5 years back or something, I started seriously looking at, can in fact LLMs solve simple planning problems? In AI planning community, automated planning community, we use block stacking as essentially the fruit fly of the simple planning problems. So in fact, this one was GPT-4o. This is more recent version of the experiment where I just asked GPT-4o, here is a simple example. Block C is on top of block A, block B is separately on the table. Can you tell me how I can make a stack of blocks with block A on top of block B and block B on top of block C, but without moving block C? If it's not too late in the day for you, you can already see that this is a problem that's kind of tricky here. Actually, you can't actually solve it because there is no way of doing the stacking without moving block C. And what's interesting in this case is, even though it's just 3 blocks, the GPT-4o, which is supposed to be like great at reasoning and planning, etc., hallucinates the heck out of every phase of this problem. Essentially, it first hallucinates the specification. When I patiently point it out to it, then it hallucinates the physics. Then when I again patiently point out to it, then it hallucinates the goal. And in general, working with LLMs with humans in the loop tends to be working with a highly apologetic, incompetent planner where you keep correcting all their errors, and in the end you want to give credit to the LLM. Normally humans don't give credit to anybody else, they can take the credit, but here it turns out that if you give credit to LLMs, you get NeurIPS papers. Okay, so this is what is actually the kind of a single example. In fact, New York Times was trying to write some story about GPT-4o when they came out, and then they took this example and actually put it up. So it's actually a famous example at this point of time. Obviously, we did more than just a single anecdotal example. I will tell you about a benchmark in a minute. But before we go there, I want to actually kind of make it clear to some of us that, to all of us, that the thing that's tricky about LLMs is they kind of conflate style versus content and form versus factuality. LLMs and generative AI in general capture the distribution of the data they're trained on. Style is a distributional property. So LLMs can learn this very easily. Correctness and factuality is an instance level property. So no learner that mostly learns distributional information is guaranteed to learn individual correctness and factuality. Civilizationally, we had always thought that style is harder than content. And so it's not surprising that when we see that LLMs output things that look like plans, we assume they are plans. But then if you actually carefully check, they actually won't execute. They will have execution problems, etc. And in general, this cartoon that I have sort of made t-shirts and I'm selling on the side of late is basically this. The whole impressive reasoning abilities of LLMs are really based on prompter knowing the answer. And so when the LLM gives out something that looks like a plan, the prompter in the loop carefully corrects it until it becomes correct and then gives the credit to LLMs. So we actually wrote a more systematic study of this behavior of LLMs in solving planning problems. There's a NeurIPS spotlight paper that's there. There is also, we provided a benchmark for these based on basically the kinds of planning problems that have been looked at in the planning community, logistics, blocks world, scheduling problems, and so on. And then we provided that benchmark that's also available, that was also published at NeurIPS as a benchmark paper. And then this benchmark also, interestingly, contains obfuscated domains. What is an obfuscated domain? In addition to normal blocks world, which is on the right-hand side, which has picking up a block, unstacking, putting down, stacking, etc., the right-hand side is a version of the blocks world where object and predicate names are changed consistently. And any of you, and given the very nice lecture on logic that you just heard, you know that in logic, changing the predicate names and changing the object names consistently doesn't change the meaning at all. Right? In fact, as Shakespeare said, a block by any other name would stack just as strong. So these two are really blocks world. One is in a different terms than the other. And if you have the internal reasoning capability, you should be able to solve either of them. And for the record, every possible, even simplest planner from the automated planning community will solve all problems for the first version as well as the second version with no difficulty. There's no increase in difficulty, whatever. And so this we call this obfuscated or mystery blocks world. And here is the killer about the current state of art about planning in terms of these LLMs right now. This is with Claude 3.5, Claude 3, GPT-4o, GPT-4, GPT-4 Turbo. Basically, as of June 20th, in fact, yesterday, Karthik was telling me that he also ran it with the most recent Claude, but I forgot to get those results in. So, but you notice that in the blocks world, which is very simple, where about 500 blocks world problems, it turns out these are all actually solvable instances. They're not unsolvable. Unsolvable ones, actually, LLMs do much worse. For even solvable instances, you see that they're not anywhere near 100%. And very sad situation is for Gemini, that in fact, which actually says it's very, very reasoning oriented, and it's like 11.3%. What's more interesting is the mystery version. That's where you obfuscate the names, where actually logically the domain is the same. All of them die. You see 3.1, 0%, 0.83%, etc., etc. So this sort of makes me think that LLMs cannot plan. And in fact, this is not the only piece of work that we have done on the limitations of LLMs about system 2 abilities. They're great system ones, but they can't do planning in autonomous mode. Chain of thought, React, etc., don't actually help. As the right-hand side, like the figures show, what happens essentially when you give, for example, a chain of thought to how to do block stacking for like 2 or 3 blocks, it does well for 2 or 3 blocks, and it dies as the number of blocks increase. It's the same thing for even last letter concatenation, which has nothing to do with planning. In general, LLMs have difficulty learning and applying procedures. So chain of thought, etc., don't necessarily change the reasoning abilities. They can't improve by self-verification. This is one of these other misconceptions people have, that since generation is harder than verification, maybe they can do verification even though they can't generation. No, they cannot do verification with any kind of guarantees. We actually show that last picture on the right-hand side, the bottom one, shows that when LLMs try to critique their own answers, their performance goes down, not up, down. That's because they actually do hallucinations, false positives and false negatives in figuring, looking, seeing errors that don't exist, or missing errors that exist in their own solutions. And so oftentimes they might even actually go right over the correct solution and end up in a wrong solution. And so it's actually, self-verification doesn't work. So this is something that I would differ from Henry's talk, where number 4 in his final slide was LLMs seem to have reflective abilities. Maybe, because it's not guaranteed in any which way that their self-reflection and their self-verification are guaranteed at all. So, and then having humans iteratively prompt is basically invitation for the clever hands effect, where you wind up solving the problem and essentially give the credit to LLMs. It also turns out that in general, the logical notions of reasoning are actually quite relevant. It turns out the usual types of inverses outer distribution are not very useful in understanding reasoning. You really want to think in terms of deductive closure, because otherwise you don't actually see the point that LLMs are failing is learning the procedure. So when you give the number of last letter concatenation chain of thought, it actually improves for the size of examples. You gave the example about how to do last letter concatenation, but as the number of words increase, it fails completely, and that's not what you expect from any reasonably intelligent system. In general, there's a longer version of this talk which talks about the limitations. That's not the main point of my talk here, but it actually, one of the points to understand is planning involves getting the planning background knowledge, and also making sure that in conflicts between actions are removed, so that actually the actions can be done in the order that they're given. LLMs are actually good at the first part, getting approximate knowledge, but they're very bad at the second part, which is resolving the interactions. And so whenever there are interactions in the domain, they die basically. And so that sort of explains why LLMs, and the other reason why LLMs are claimed to do planning and reasoning, it turns out is oftentimes you can confuse retrieval for reasoning. If I give you a whole bunch of problems and their answers beforehand, and then somebody else asks you how to solve this planning problem, and you're able to approximately retrieve from the number of problems that you've been trained on, that didn't involve reasoning, it involved actually retrieval. And in fact, if you had a system 2 which actually solved those problems and then compiled it into system 1 and you retrieved it, you get the credit. But here, essentially, you are actually being given the solved problems from outside, and that basically can be confused for reasoning abilities. In general, LLMs approximate retrieval appends our intuitions about what is reasoning versus retrieval. This is a fascinating topic in itself. There is a 2-hour tutorial that I gave at ICML that you can look at. And there's also a 1-hour version of the overall tutorial that I gave as an invited talk at ACL that you might also look at for understanding more about LLM's current limitations in planning things. And if you want the more philosophical connections, you can take a look at this machine learning street talk. But then that comes to the more interesting part, which I have some time to talk about, which is, can LLMs help in planning at all? Is it like they're bad at autonomous modes? Can they but still be helpful? It turns out LLMs are great idea generators, are muses. And as I said, traditionally, most other AI systems have been essentially good at capturing deeper narrow system to behavior. LLMs are our first broad and shallow system 1, and you should be able to combine them. You can take the ideas that LLMs give and verify, and then if they're wrong, send them back to LLMs, so that there's like a bidirectional interaction of back prompting from the verifiers to LLMs. And that would actually be a very sane use of LLMs. Also, another thing that I want you guys to think about is, there's this old idea of knowledge engineering where a human goes and human knowledge engineer goes and talks to domain experts and looks at the expertise and writes them as rules and then writes them into a knowledge base, and then some logical reasoner actually reasons about them. This was obviously had its own problems, the whole expert systems direction. You can think of what actually LLMs did as approximately short circuit that whole yellow region. You can ask LLMs about what you might have actually asked domain experts, and you can get reasonably correct approximate knowledge. And with them, if you have human experts in the loop, they have much less work to do. So they can become essentially co-pilots for knowledge engineers. And that is another great use of LLMs. So when I said LLMs can't plan, I do mean that they can't plan in autonomous modes, but there is a green part that they can actually support planning in what I am calling these LLM-Modulo frameworks, where LLMs are universal idea generators about domain models, idea generators about plans, idea generators about problem completions, and there are external verifiers, some of which themselves can actually be built by asking LLM for the approximate knowledge to build those verifiers. Essentially, external verifiers can be procedures, in which case you can be using LLMs as sort of co-pilots to make those procedures, and you correct them and then use them as the verifiers. And then once you have this, essentially LLMs, the generative powers are being used to actually check with the verifiers, will check what is wrong with what is currently generated. And if there's anything wrong, they send it back as a back prompt to the LLM. And this will then come up with a new candidate. And then there is this nice generate test framework that goes on. And obviously, generate test is a dumb idea from a pure search point of view, but it can be a great idea if a generator actually has a higher density of plausibly good solutions, which I believe is one good thing LLMs actually have, because they've been trained on huge footprints of our data on the web. So in general, so that basically is LLM-Modulo architecture, where the LLMs are in the middle. They can be helped to, in problem specification stage, in the domain model extraction stage, and also most importantly, on this generate test stage. And then on the right-hand side, you have a bank of critiques. The correctness critiques cannot be played by LLMs. As I pointed out, they can't check correctness, but the style critiques can actually be played by LLMs. I'll mention that in a minute again. And so this basically is the LLM-Modulo architecture. If you take it to the bare bones and just have one single critique and apply it, let's say, to the blocks world problem, you will notice, we noticed, and we actually described this in the NeurIPS paper in 2023, that blocks world, the blocks world performance improves up to 82% with just 15 iterations between the external verifier and the LLM. And that's pretty impressive. It's only 15 iterations. And so if you increase the number of iterations, you do better work on the connection between the verifiers and the LLMs, you can do much better, which is part of what we're doing. So the bank of critiques part, I wanted to mention that there can be correctness critiques and style critiques. In general, anytime you have a combinatorial solver, it essentially inverted a correctness definition. That's basically what all combinatorial solvers are. And in general, combinatorial solvers had hard time figuring out how to capture the style constraints. So for example, they can give you a travel plan that is valid, but they don't know whether it is a reasonable travel plan. It might very well be a plan which involves like some part is by car, some part by train, some part by walking, some part by hitchhiking, some part by blah, blah, blah. And finally you reach, let's say, San Francisco. That's a valid plan, but that's a sucky style with respect to what humans expect. And so there was all these other ways in which you try to bring in the style constraints, like hierarchical task networks or preference capture, etc. One thing that LLMs are good at is they actually approximately capture the preferences that the humans have, because they've been trained on the human footprints. And so for the style critics, we actually can use LLMs themselves as the style critic. But the correctness critic, you wind up using this, basically external verifiers. And the critiques can be binary. They can also be constructive. They can point out errors in the candidate. They can also suggest local repairs, saying, consider adding this piece to your your candidate. And then the meta controller combines these criticisms, and it can have actually, there's a LLM role there too, and then improves the performance. So talking about the style critiques part, LLM behavior critiques have been used. We have used them to catch, like, for example, undesirable robot behavior. So, for example, you ask a robot to give you like a pair of scissors. Giving the scissors is basically goal achievement, but giving the scissors with the pointy end towards you might be goal achievement, but with undesirable behavior. These are the kind of things actually VLMs basically are able to actually catch quite reasonably. And so there's actually a Comb paper that's coming up in October that discusses how LLMs can be behavior critiques for style critiquing. And then you can also be style critiquing for human preferences in terms of human AI interaction sorts of things, such as, is the plan, the behavior that I'm coming up with, is it going to be surprising to the human? Is it going to be explicable, and so on? And it turns out there's a reasonable accuracy that LLMs can give for that. And so this will be an inbuilt critique for the solver in terms of whether or not certain kinds of behaviors would be reasonable and interpretable to the humans in the loop. One other thing I want to point out is we are using critiques rather than solvers. We could use solvers, but I think that's like a single directional interaction. Solver is really verifier plus search, inverted a verifier and doing the search. And I think that it's a much better way to compose multiple verifiers and extend the scope of the kinds of problems that you can solve. As again, as just saying, I will do this single directional interaction where LLM figures out the syntax for the solver and throws the syntactic problem to the solver, and solver does whatever it can do. And that's not as useful. Soundness and completeness depend on the soundness depends on the verifier, correctness verifiers, soundness. And the completeness, of course, depends on LLM's ability to generate candidates. And we talk, about how you can actually improve the soundness by diversifying using diversifying prompts that actually push LLM to generate candidates that are in different parts of what would have been called search space. So in addition to the Bloxworld kind of a thing, there is this travel planning benchmark this outside people have come up with, which is from NLP community, which is actually a scheduling benchmark. They show that GPT-4 does 0.6% well on that benchmark. That's extremely bad. And scheduling actually is the worst possible thing LLMs can be subjected to, because scheduling is all about interaction resolution. And we actually took that benchmark and we applied LLM-Modulo, and we actually can significantly, with just 25 iterations, significantly improve the performance by like 5 or 6x improvement in terms of the accuracy performance. Another one was from Google.
Sorry, I hate to cut you off, but just maybe 1 or 2 minutes.
Yes, 1 or 2 minutes is what I'm going to take. Another thing is this natural plan benchmark that Google DeepMind just put out. And this is actually, I don't know why they call it planning. It's really scheduling. It's trip planning, meeting planning, and calendar scheduling. And the thing that makes it Google, I think, is they have the Google Flyer and the Google Maps and the Google Calendar. They too actually show that on the scheduling problems, LLMs die pretty badly as the size of the problem increases. And we take these problems and again apply LLM-Modulo, and we can significantly improve the performance with very small number of back prompt iterations. Just 25 back prompt iterations, you can improve the performance quite significantly. And so this is a sane way. LLM-Modulo sort of unifies all sane users of LLMs, in my view, in reasoning problems. The alpha geometry, alpha proof, fun search all use LLMs as idea generators with external sound solvers and verifiers. They spend enormous resources fine-tuning the LLMs to improve the density of good guesses. They're not improving the reasoning power, they're improving the density of the good guesses. The program synthesis community is also, I think, a little bit of that probably Francois will be talking about. They're also very sane people. They realize that you don't just give the piece of code that LLM guesses as the correct code. You actually have unit testing. Unit testing is a partial verifier. And so if it fails the unit test, then you know that the code is wrong. If it passes, it may still be wrong. At least it passed the unit test. You can actually use LLM-Modulo architecture recursively also to construct the domain models. There's a paper in NeurIPS 2023 that shows how you can get the planning domain models themselves by actually querying LLMs with partial human help. And that's a way of actually improving the knowledge acquisition part of these kinds of planning problems. And one last thing I want to mention is in this LLM-Modulo framework, while humans are involved, we avoid humans in the most time-consuming inner loop, which is the search loop where generate test part. I think life is too short for us to be part of combinatorial search solvers inner loop, and so I don't want to have that happen. You can always use LLMs for format change and specification. We use this in this larger architecture, but using them just for that seems to be sort of being under ambitious about using LLMs in reasoning problems. The last thing for this crowd, it's not just, I'm not just adding LLM for the heck of LLMs. It's actually going to expand the scope of the problems that the traditional systems were able to solve, because now you allow any arbitrary free-form specification of the problems and do the best you can in terms of verifying the correctness with a bank of pre-clicks. So that's the summary. LLMs cannot plan in autonomous modes, but they can plan in this LLM-Modulo frameworks. There's a bunch of papers that you might be interested in looking at if you are in detail, if you're interested in details. Like I said, there is a 2-hour tutorial in ICML and a 1-hour keynote talk at ACL that you might be interested if you wanted more details. And then finally, as I said, there's this ML Street Talk thing that talks more about the background philosophy. That's basically all I have, and I'm going to just stop. Thank you for your time.
Thanks, Rao. And